The first thing we're going to learn about before we get any further with CellNav is the principles of the celestial sphere and the different coordinate systems that you use. Because for CellNav, you cannot just work with latitude and longitude. It doesn't apply in all cases. It's not relevant to everything. And so you're going to constantly be shifting between three different ways of measuring arc on a sphere. Before we touch on that, though, firstly, the celestial sphere. Just like how we have to pretend that the Earth is a perfect sphere for TNAV to work most of the time for plotting to be accurate, we have to pretend, I mentioned this before, but we have to pretend that the Earth is the center of the universe, that all of the bodies revolve around the Earth, and that all of the stars are fixed points on a larger sphere. Basically just like ignoring everything that Copernicus ever said. And the way that comes out looking is you can imagine that the Earth has a larger sphere surrounding it called the celestial sphere that all of the stars are just imprinted on, meaning all of the stars are equally far away from Earth. There's no difference in distance. They're all just the same distance away, and they all move as one. So when as the seasons change and the positions of stars change in the sky, they don't change relative to one another. That's why the constellations are always the same, look the same. They all move as one group. Now that's the stars, but you've got the sun and the moon and all of the planets, and those move on their own. That's why they were noticed as different by, ancient astrologers. That's what the difference between a planet and a star was originally, is that the planets all go in their own directions, doing their own thing. The moon is obviously constantly rotating right around the Earth, and the sun is following its path, which is technically called the ecliptic. So they're all moving on their own. They're separate from the celestial sphere and technically imagined as being inside of it. Something that confused me for a long time was how you could see into the southern hemisphere, at least from, the United States, see stars that are in the south. And I think it was because when I first imagined the celestial sphere, I imagined like, here's the Earth and here's the sphere. It's like they're basically the same size, and so your field of view would only be about that big on the sky, but it's not. The celestial sphere you should imagine as being substantially larger than the Earth, so that if you're sitting here, you can see basically nearly half of it on your own without a problem. Probably, actually, no, more than half of it should be visible to you at any given time, and so therefore you can always see into the northern hemisphere or the southern hemisphere. So that's the celestial sphere. Now, latitude and longitude only really exist on the Earth. It's got its grid system that it uses for objects that are physically touching the Earth. It does not necessarily apply to the celestial sphere. Now, what you can do is you can project the sun's position down onto the Earth or a planet's position down onto the Earth and say where it is directly above, where it would be if it landed on the Earth, but it's not technically there. It's here. It's out here somewhere. This here, where we're imagining the sun would be, is called the geographic position. And that's the one part of CellNav that can be applied for the normal latitude longitude system of measuring the surface of the Earth. Is it the geographic position of a body? But that's just a projection down onto the Earth. The other two systems we use, firstly, are the horizon system, and then I can't remember its exact name, but we'll just say the time system. Now, at the we'll do time first because it's kind of easier to explain in this regard. if all of the stars move as one, the only thing that really is needed to define them is how long it's, in what way they're moving. They're always just rotating around the Earth, and what the planets are doing at the same time. And we just measure that as the difference in time that it takes for them to be, for instance, at Greenwich, how far away they are from Greenwich in time. So if we've got the Earth here and here's the prime meridian, we wouldn't say that something's longitude, like for instance the sun. Its longitude is not how far east or west it is from the prime meridian. Instead, we'd be talking in terms of time and its degree value, as you could then convert that to time. So usually these are called hour angles as opposed to longitude. In this case, it would be the GHA, the Greenwich hour angle, but you could also have the local hour angle, there's a couple others, but it's just, it all is broken down into time. And so how long this in total takes is, of course, 1 day for the sun to rotate around the Earth. And you can think of it as just intervals of certain hours, not necessarily longitude. It's not the same thing. And you can kind of imagine a full meridian swinging around the Earth and not just the sun moving in place. It's this whole meridian is what the sun's hour angle is. And if the sun was over here, then this whole meridian would be it, not a specific point. The horizon system is about measuring what a person can actually see. And usually the best way to imagine this is to just show the Earth like that with a little guy standing on it. The horizon system is everything visible to them, defined off of them. So the top of the horizon system is not the North Pole like it is in the normal latitude longitude system. The top of the horizon system is you. It's the point on the celestial sphere that you are directly beneath, and that is called the zenith. And if we were to go to the other side, so the antipode, I wish I had more room here, the opposite side of the celestial sphere, exactly 180 degrees around from the zenith, is called your nadir, but that's not necessarily that important. You never really work anything off of that. The point is, the horizon system is measured from your position. It doesn't matter what north or south are. The equator could look like this, and the North Pole could be over here. None of that's important. All that's important is what is visible to you and what that angle is, either up from the horizon or down from the zenith. That's really how you define individual bodies. So if you were taking a shot of a star here, you would measure its altitude, which is its height above the horizon. And you can see here, by the way, that the horizon is a little bit lower than what looks like actually halfway between, from like exactly 90 degrees away from the zenith. And that's because when you're, as we just stated, you can see more than half of the celestial sphere at any given time, because you can kind of see down an angle like this until you hit the hit the curve of the Earth. So you can see more than 90 degrees from the zenith to the horizon. So we have a distinction between the visible horizon, which dips down below 90 degrees, and then the celestial horizon, which is exactly 90 degrees from the zenith to the horizon. That's actually splitting the celestial sphere in half, defined off of your position, whereas the visible horizon is a little bit lower than it. So there, you have to do some corrections to fix them around, but then what you would be doing eventually by taking a shot of the star is measuring its height above the celestial horizon, and then using that for your calculations. And then this star would just be defined off of its height above the horizon, and later you would then go to its back to the time system here and calculate its GHA, its LHA, whatever its hour angles you're going to be using. And then between those two, you would eventually be able to then plot on the Earth. So the point of all of this being that you have to switch between these three systems all the time while using CellNav. You have to have a pretty strong understanding of them. I'll go into more detail on each, but it does help to have a sort of outside view of all of them interacting with one another.